Okay, this video is for AP Calculus BC, and it's for additional properties and techniques related to finding limits analytically, specifically. So in the last video, we learned that there are three different ways so far that we've learned to be able to analyze or compute what a limit is. We can always use, and this method will always work, we can use a table of values. That's called evaluating numerically, by literally plugging x's below and x's above the target value to see if the y's are approaching a value. That's the same from both sides, so we can declare the limit exists. If you're provided a graph, or you can easily graph the function, you can use the graph to determine if the y's match as you approach an x value. But most frequently we try this because it's the most computationally efficient, by literally plugging in the target value. If the results are defined when you do that, you get a finite number, then that is the limit, because that means the function's well behaved enough that plugging in from the left and the right would give that same value. But if the result is undefined, specifically if you're dividing by 0, and that means you can try either factoring or synthetic division to enable factoring to try to get the offending part of the denominator that's going to 0 to factor and cancel out, so you can successfully plug it. All right, a couple of properties to know. The textbook here defines a number of good properties to know. If you have a constant and you're taking the limit as x approaches anything, that's just the constant. This is sort of intuitive. If you have a function which is simply a constant, like y equals 4, then it doesn't matter what x you're plugging in, you always simply get that constant as the limit. If you have a function that's y equals x, that's what this is saying, then as you approach any particular x value, the y is simply the same value, because y is the same as x. But these two properties are really important, these next two, which say if you have two terms that are either separated with addition or subtraction, you can think of each of those as a separate function. You can take the limit separately of each term's function and then just recombine them by adding and subtracting. And unlike with derivatives, you can also do that for multiplication or division. So if you have a function that can be split into a factor times another factor, you can simply take the limit of each factor and you can multiply the results together. You don't have to do something like a product rule like we do for derivatives when we're talking about limits. And then if you have a function inside of another function, you can take the limit of the inside function and then plug the result of the limit into the outside function. That's useful. For example, let's say you're taking the limit as x approaches 0 of the square root of 1 over x squared, right? You can first take the limit of 1 over x squared first, and then you can plug that result into the square root function. That's also quite useful. All right, so let's look at how you can use these properties in general. Let's say you're finding the limit as x approaches 2 of 2 times f of x plus 1 over 4 minus g of x. And then we have graphical representations for f of x and g of x. All right, so I'm going to write all these steps out really formally, although you don't have to do as formal as this. This limit, first of all, is we can take a limit of the divisor over the limit of the numerator. So I can separate this way. I can say that there is a limit as x approaches 2 of this 2f of x plus a limit as x approaches 2 of 1, and then I can take the limit as x approaches 4 of 4 and limit as x approaches 4 of g of x. In other words, you can take a limit of each piece. You can take a limit of the numerator, a limit of the denominator, and divide the results. And then within each of those, you can take the limit of each thing. And actually, this 2 can come outside of this as well. So we can instead write that as the limit 2 times the limit of f of x. Okay, so let's evaluate each of these things. I'll switch colors here. This is a 2. This here, this limit as x approaches 2 of f of x, I'm going to evaluate graphically. So as x approaches 2 from the left and the right, the blue function here is the f of x function. It looks to me like that is approaching 2 from both sides here. So this limit evaluates to a 2. So I can replace that entire limit with the result of the limit, which is a 2, plus the limit 2 of 1. That's just saying if the function is always 1, as x approaches 2, what do we get? Well, when we have a constant, we just simply get the constant. The limit of 4 is 4, no matter what we're approaching. This is the limit as x approaches 2, so I wrote that incorrectly. And the limit as x approaches 2 of g of x means if for this limit, we're going to go to the g of f function, this purple function, and say x is approaching 2. Looks like the y is approaching 3 from both sides here. So that's going to be minus a 3. And that means we have 4 plus 1 is 5. 4 minus 3 is 1. So this limit is 5. This limit is equal to 5. It just means that you can treat these limits almost as if they're just algebra, they're just numerical values, because when we evaluate them, they are if they evaluate to a number. So that's the why we have to have these properties, so we can do more complicated limits like this by finding individual limits of pieces. All right, so now that we've got that, let's take a look at a couple of additional things you can do for analytical besides factoring, which is the main one. This is the main one that we often have to employ because we're frequently dividing by 0. But sometimes if you have a radical, you can do rationalization, and sometimes when trig functions are involved, we can do special trig limits. So here's an example where we'd use rationalization. I have a square root here. If I try plugging a 9 in here, the square root of 9 is 3. 3 minus 3 is, we're about to divide by 0, so that's a problem. But what we can do is we can rationalize this by taking whichever side has the square root and writing the conjugate, multiplying the top and the bottom by the conjugate. So the conjugate is the same two things, but you change the sign. So if that's a minus, this is a plus. And then we're actually just going to be multiplying numerator and denominator by this, so that we're really multiplying by 1. The top currently here is x squared minus 81. Okay, so this is equal to the limit as x approaches 9 of, I'm not going to multiply that out. It's x squared minus 81 square root of x plus 3. But on the bottom, I am going to multiply this out, because if you multiply a square root of x times the square root of x, let me actually write it out. Square root of x times square root of x, we'll do FOIL, plus 3 times square root of x, minus 3 times square root of x, negative 3 times positive 3 is negative 9. With with these conjugates, you would get the middle will always cancel, and the square root of x times the square root of x is just the square root of x being squared, which means it's just x. So this ends up being algebraically equivalent to this. Limit as x approaches 9 of x squared minus 81 square root of x plus 3. And then here we have x minus 9. Now, we're still dividing by 0. If I plug a 9 in here, I see that. But I also have this, which can be further factored. So that can be factored into, by difference of squares factoring, x minus 9 times x plus 9 times the square root of x plus 3 over x minus 9, which means that this x minus 9 can cancel, and we're left with limit as x approaches 9 of, there's no more fraction, it's just x plus 9 times the square root of x plus 3. And now I can safely plug in 9. I get 9 plus 9, and then the square root of 9 plus 3. So that is 9 plus 9 is 18. Square root of 9 is 3. 3 plus 3 is 6. And let's see, 18 times 6 is 108. So this evaluates successfully to 108. So that procedure is called rationalizing. Whenever you have anything with a radical, you can attempt to move it to the other side by multiplying by the conjugate of that. And sometimes, not always, but sometimes that will result in cancellation of the problem that's causing us to divide by 0. Okay, another case that's sometimes useful is using what we call the special limits for trig. There are certain predefined limits that we can sort of memorize their form. If you are taking specifically the limit as x approaches 0 of a fraction that has sine of a constant times x over that same constant times x, or if it's constant times x over sine of constant times x, you'll get a curve shape that looks like this. Actually, this one looks like this. Looks kind of like a peak here at 1, and then it kind of oscillates around 0 after that. But that means that as we're approaching 0, graphically, by graphing this function, we are always approaching the value 1 on the left and the right. So that means this specific special trig limit can be immediately replaced with this memorized result of 1. And occasionally this one is helpful as well. If you graph this particular structure, cosine of any constant times x minus 1 over that same constant times x That's equal to 0 because of the curve shape. And then we're asking people to memorize these two cases, but particularly this one is useful. Let's see how we would use that. If we wanted to evaluate this, as x approaches 0, the tangent of 5x, if I just look at the denominator here, tangent of 5x is the same as sine of 5x over cosine of 5x. And as we're approaching 0, we're nearing 0 from the left and the right on the number line. This is the point 1, 0. So the sine is approaching 0 and the cosine is approaching 1. 0 over 1 is 0. And that means we're about to divide by 0 here. So we're going to have to do something. Okay, what I usually do is I first split the tangent of 3x over 1 separate from the 1 over tangent of 5x. And then I replace each of those with sine and cosine. So this is actually equivalent to, the tangent can be rewritten as sine over cosine. And I'm going to separate those this way. And then this 1 over tangent is cosine over sine. So I'm going to write the cosine of 5x over 1 and 1 over sine of 5x there. All right, so how does this help? Well, if we try to evaluate the sine, since we're plugging a 0 in, the sine of 0 is 0. 0 over 1, that's actually okay. Cosine of 0 is 1, so that's 1 over 1. That's okay. These are multiplied. Cosine of 0 is 0, 1. That's 1 over 1. That's fine. But the problem is this one. This is 1 over sine of 0, which is 0. That is the problem. All right, so to get rid of this, we're going to try to balance that out by making it look like this special form or this special form. If I have the sine of 5x on the bottom, I need to put a 5x on the top so that that limit as x approaches 0 turns into a 1. And that means I'm going to multiply by 5x over 5x. Okay, now why are we going to do that? Because if I do that, if I multiply by 5x over 5x, I can take this 5x and put it over here. Okay, if I do that, it goes away from here, that just becomes a 1. Right? And then now I have a new result here. Instead of, let me erase this, instead of this being 1 divided by 0, now it's 5x, it's this 5x over sine of 5x, which is a special memorized limit that we know is equal to 1. So this now becomes a 1. But now we've shifted the problem. We have this extra factor, 1 over something going to 0 out there. So now this is the problem. Whereas before this was the problem, now this is the problem. So to get rid of that one, we're going to do another balancing act. I'm going to do that by saying there's another sign in here, over here, which is 3x. So if I multiply by 3x over 3x, I can take this one and move it all the way over here, so that this gets changed to the special limit of 1. And then this 3x can go on top of this. So let me write what we have at this point. Let me show you exactly the way I would actually do this. We have limit as x approaches 0. Originally we had this 3x over 1, 1 over cosine 3x, cosine 5x over 1, 5x over 1, 1 over sine of 5x. Everything's okay except for this one. So what we do is we balance that by putting a 5x here and balancing it with a 5x out there. But because we have to get rid of this, I look for another sign, and there's one over here. I can balance this one with a 3x over 3x. This limit now turns into a 1. This limit is 1 over 1. This limit is 1 over 1. And this special limit is also 1. And now these final two x's can cancel out and leave me with 3/5. So I have 1 times 1 times 1 times 1 times 3/5. And that means that this whole limit is equal to 3/5. Now later on, after we have derivatives defined, we'll have a different way to do this with L'Hopital's rule that's easier. But for right now, this is the one way that we have to evaluate that one, using these special trig limits. not frequently used, but something that's officially part of the course. Here's another one. You can give this one a try, similar to the one we just did. See if you can split this up and combine things in such a way that you can use those special trainings. So pause the video, give it a shot, and unpause it. See if you're ready. Okay, what I would do here is rewrite this as limit as x approaches 0 of cosine of x. Tangent, I'm going to split into sine of x over cosine of x. And then I've got this 1 over x here. And then I'm going to note something. The cosine of x over the sine of x, those two cancel out because they will form a 1. And then I have a sine x over x. So this is equivalent to limit as x approaches infinity of sine of x over x, which is one of my special limits. And so therefore it's just equal to 1. Okay, another thing that can be invoked, although not frequently used, honestly, is something called the squeeze theorem. Sometimes it's difficult to evaluate a function's limit directly, but you can show that that function's value is always between two other simpler functions whose limits are easier to evaluate. So let's say you have a really complicated function, this black function here, f, and it's difficult to evaluate directly. But I can show that it's always underneath this simple function g, and it's always above this simple function h. If you can show that h and g both have a limit of some number, then that means that since f is squeezed in between h and g, it has to have the same limit. Here's the formal theorem. If the target function f of x can be shown to be always greater than a function h of x and less than a function g of x for all x in an open interval containing the target x value c, except possibly at c itself, and if the limit of the lower function is equal to L and the limit of the upper function is equal to that same number L, then the limit of the middle function, I'm sorry, that's a typo here, this should be F. The limit of the middle function f of x exists and is also equal to that F. All right, so that's called the squeeze theorem, or sometimes called the sandwich theorem. Some books call it the sandwich theorem. So let's see how we could possibly use that here. Use the squeeze theorem to show that the limit as x approaches 0 of x squared of cosine of 20 pi x is equal to 0. Illustrate that by graphing these other simpler functions. F of x is negative x, and h of x is positive. Negative x squared and positive x squared on the same screen. All right. So here's the idea. This is pretty complicated. We have x squared and a cosine. Would you agree that this cosine here, if you plug whatever x is, you're always going to get the cosine is going to be somewhere between -1 and 1. So this value is somewhere from -1 to 1, somewhere in that range. And that means that that times x squared is always going to be somewhere between negative x squared and positive x squared. Right? So like if this cosine was 0.8, it would be 0.8x squared. And that's somewhere between negative x squared and x squared. So to show you what we're saying here, let's actually graph this with a calculator. So I'm going to bring a calculator up here. And let's plug in the target function. So I'll do that. The target function is x squared times cosine of 20 pi x. So if we just graph that, let's graph that from, well, let's just do zoom 6 first. That's origin plus or minus 10. It's going to be kind of crazy looking. No, it's not too bad. Let's figure it out. Okay, so there's this really crazy function there, right? That's this function. Right, but I'm asserting that because cosine always goes between -1 and 1, the lowest this will ever be is -1, which means that if I make this just -1 times x squared, and I put a function in here for that, negative x squared, and I add that onto this graph, that function is always below this complicated function, okay? And if this can never go above 1 times x squared, we'll put another function on here, which is positive x squared. That's this function here. And so sure enough, this function is always in between negative x squared and positive x squared. All right, so how will the squeeze theorem allow me to evaluate this limit? Okay, so what we can say is, let me write it this way. X squared cosine of 20 pi x is always less than or equal to x squared and greater than or equal to negative x squared. Right? And then you can also say the limit as x approaches 0 of negative x squared, we can evaluate by plugging in. If I just plug a 0 in here, I get 0. And this simple function here, the limit as x approaches 0 of x squared, gives me 0. And since those are both the same, you can therefore say, therefore, that 3 dots means therefore, by the squeeze theorem, the limit as x approaches 0 of x squared times cosine of 20 pi x is also equal to 0 because it's squeezed in between the two to also be equal to 0. All right, so that's an example of the squeeze theorem. One last example here for us. This says evaluate the limit as of f of g of x as x approaches 3, and then they give graphical piecewise function definitions for f and g. All right, so the first thing is we're going to use a property that says that this is equal to f of the limit as x approaches 3 of g of x. But because this limit affects x, and x is being plugged inside g, you can take the limit first of g of x. So let's use the graph to evaluate that. As x approaches 3 from the left, the g curve here approaches 2. And as x approaches 3 from the right is also approaching 2, so I think I can declare that this limit is 2. And therefore, I can now plug exactly 2 into this function f. So this is the graph for f. So if I plug 2 in, I have an open circle here, but I have a closed circle here. So that means that this is actually equal to 3. So therefore, this limit is equal to 3. Is that right? What do you think about that? I think we've got to be a little more precise. Let's take a closer look. I'm looking at my notes and I'm seeing something a little bit different here. Yeah, let's be a little more precise here. All right, so let's go back to where we originally said here. We have f of limit as x approaches 3 of g of x. Okay, so if I take the g curve and I approach 3, let me actually be more specific here. I'm going to use some simple notation here. I was a little relaxed about this. As we approach 3, the limit as x approaches 3 from the left of g of x is 2. I think that's true, but notice that it's approaching from the left. So I'm going to actually put this as well. This is really approaching true from lower values. And on the right-hand side, limit as x approaches 3 from the right. So as I approach 3 from the right here, I'm also approaching 2, but I'm specifically approaching 2 from lower values. Okay, I think that's going to turn out to be important. So this is a number 2, but because it's a limit, it really is x is approaching 2 from lower values as the result of this. So I really have to now say, let's take the limit as x approaches 2 from the left of f of x. Because I'm not literally plugging that value in. I'm approaching 2 specifically from the left, which means actually I should be getting -1 as the output, not 3 that I mentioned before. That's a subtlety, right? We really are not actually plugging 3 in, which means I really should be talking about the behavior of x approaching 2, and then what happens over here as x approaches 2 specifically from the lower values. All right, a subtle little problem to finish off the lesson. Right, summary. What did we talk about today? We basically just said that there are a number of properties that mean you can evaluate more complicated limits by splitting them into parts and treating them kind of as numerical values. But be cognizant about how x is approaching values. And then we added on that you can rationalize something sometimes or using special trig limits to evaluate without having to resort to plugging in numbers. And then we talked about the squeeze theorem as well, that sometimes you can evaluate a limit by finding bounding values that are easier, bounding functions that are easier to evaluate the limit, and if they evaluate to the same value, the middle value is approaching that same value. All right, that'll wrap up this video.